So it's a pleasure. Welcome, everyone. I'm delighted to introduce Sam Lin from Dartmouth College, who will speak on three-dimensional geometric structures in the Laplace spectrum.
Thanks for the introduction. First, I'd like to thank the organizers for the invitation. And I'm very thankful to be able to talk to people from all over the world about my topic today, three-dimensional geometric structures and Laplace spectrum. And first, I have to admit that this is my third Zoom meeting for today. So if I don't make sense at any point, please feel free to interrupt me to ask me questions or clarification. Okay, so what do I mean by three-dimensional geometric structures? To me, geometric structures are just a Riemannian manifold with a locally homogeneous metric. And then I'll also talk about Laplace spectrum here. Okay, so what do I mean by Laplace spectrum? So in this talk, I'm going to let M and G be a closed Riemannian manifold without boundary. And I'm going to let this to be the Laplace Bernoulli operator, which is defined as Laplace f equals to minus divergence of gradient of f. And real number lambda is called an eigenvalue for this operator if you can find a non-zero function f such that Laplace f is equal to lambda f. The collection of these values, eigenvalues, are called is called the spectrum of the Laplace operator. And since we have a closed Riemannian manifold here, Laplace spectrum can be expressed in this way. Okay. Any questions? All right, so what is the idea of inverse spectral geometry? In inverse spectral geometry, we want to study how the set of analytic data relates to the geometry of underlying manifold. In other words, we ask, can one hear the shape of a drum? So of course, at this point, we know that the geometry of underlying manifolds is not completely determined by the Laplace spectrum, but we can still try to find properties that are determined by the Laplace spectrum. So inspired by this question I mentioned by CAC in the beginning, a minute ago, a geometric property determined by a Laplace spectrum is called an audible property. So examples of audible properties includes a dimension, total scalar curvature, and the volume. Okay. So the first motivation for studying Laplace spectrum and geometric structure is the following. So one of the first inverse spectral geometry result, one of the first results in inverse spectral geometry is the following. So if you take M and M be two compact isospectral, which means that they have the same Laplace spectrum of dimension 2 or 3. Now suppose that M has constant curvature K, then N also has constant curvature K. And now you can ask, okay, can I generalize this theorem, right? So to generalize this theorem, I'd like to remind you that we have these simpler spaces in Riemannian geometry, or you can also think of them as spaces with large amount of symmetries. So we have constant curvature space. This is a subset of locally symmetric spaces, spaces with parallel curvature tensors. And all these spaces are locally homogeneous spaces. And by a theorem of Singer, we know that the universal cover of these spaces is homogeneous. Which means that if you pick any pair of points inside of this space X bar, there exists an isometry carrying one to the other. So then the question could be, okay, can I hear these simpler spaces among all Riemannian manifolds? Right? Can one hear simpler spaces among all Riemannian manifolds? This problem is extremely difficult. So on the positive side, we can ask, is the property of having constant curvature audible? And there is a result from about 50 years ago saying that this is true when the dimension of the manifold is less than or equal to 5. And for higher dimensions, in dimension n greater than or equal to 7, we don't even know whether it's possible to hear the round metric as n. So it's quite hard to prove this kind of result. And on the other hand, of course, we ask whether we can hear locally homogeneous spaces. And on the negative side, we have this important result tells us that in dimension 10 or higher, local homogeneity is not audible, which means that I can find manifolds M1 and M2. One of them is locally homogeneous, the other is not, but somehow they have the same Laplace spectrum. Any questions?
Yes, I think for the local homogeneity, for the universal cover to be homogeneous, you need completeness.
Yes, sorry. The manifolds I mentioned today are complete. Okay, so now maybe we can change the question a little bit and ask, okay, suppose I stay within this family of simpler spaces or spaces with large amount of symmetry. We can ask, to what extent can we distinguish these simpler spaces by their Laplace spectrum? And we can also ask, is the property of being locally symmetric audible among all locally homogeneous manifolds? So that's one motivation for studying Laplace spectrum and the geometric structure. Now, the second motivation comes from the relation between the Laplace spectrum and local geometry. So I'd like to remind you that the first isospectral example, but not isometric example, is given by Milner. So Milner construct two different distinct tori, non-isometric, yet they have the same Laplace spectrum. So these examples actually share the same local geometry. They have the same universal cover. Then one natural question people can ask is, does the Laplace spectrum determine the local geometry of compact Riemannian manifolds? And the answer is no. And we have examples showing us that we have isospectral manifolds, sometimes with different local geometry, and staying within local homogeneous spaces doesn't help. We can find two different local homogeneous spaces with different local geometry, yet they have the same Laplace spectrum. So the examples of isospectral manifolds with different local geometries exist in dimension 4 and higher. And of course, we want to ask what happens in dimension 2 and 3. And we also want to stay within the locally homogeneous spaces. So here is another problem. Does the Laplace spectrum determine the local geometry of locally homogeneous manifolds in dimension 2 and 3? Any questions? Okay, I'd like to move on. So to answer this question, this terminology from three manifolds is quite useful. So now I'd like to introduce geometry and geometric structures. So what do I mean by a geometry? to me, geometry is a triple. We need a simply connected manifold of dimension n. And I need a connected Lie group G. And lastly, I want a smooth transitive effective action with compact stabilizers. And this condition is kind of just baked in here because we want to discuss Laplace spectrum for compact manifolds. So we want this action to satisfy a special property. We want a subgroup of G acting properly discontinuously on X such that X quotient gamma is compact. In other words, X admits a compact quotient from this action. Then we call this triple A geometry. Any questions? Okay, so when the action is implied, we sometimes omit this alpha and just denote the geometry by xg. Note that since we have compact stabilizers, so given any geometry xg, we can always find a G invariant metric on X by averaging, okay? And we denote this set of invariant metrics by Rg of X, okay? So here are some examples of geometries. We have the geometries from the constant curvature spaces, Rn, Hn, and Sn. And the isometry group, actually connected component of the isometry group, acts transitively on these spaces, and they satisfy these conditions. Okay. Now, what do I mean by a geometric structures? Like I said in the beginning of the talk, we define geometric structure to be simply a compact Riemannian manifold MG, and G is a locally homogeneous metric. Okay. So if you have such a geometric structure, then the universal cover is homogeneous. Okay. And we say that M is a geometric structure modeled on XG if this group G here acts as isometries on this universal cover. So here I'd like to remind you that M is always modeled on the universal cover with the connected component of isometry group. Okay. All right, so what are the two-dimensional geometric structures? Two-dimensional geometric structures are just surfaces of constant curvature. They are modeled on R2, H2, or S2 geometry. And here we have this picture. Constant curvature spaces agrees with locally symmetric surfaces and agree with locally homogeneous surfaces. So to classify three-dimensional geometric structures, I think the following examples is quite helpful. So let's consider SU2, or Lie group of unit quaternions. And I want to equip them with a left invariant metric, G. And now let's fix a bi-invariant metric, G0, and define this inner product to be the restriction of G0 at the identity element. And at the identity, I know that this, this is also, okay, so this is defined as the restriction of G on the identity. So on the identity, at the identity, I can write xy as inner product of ax, y, where A is a linear map from SU2 to SU2, self-adjoint with respect to this inner product. So important result to keep in mind is that two left invariant metric on SU2 are isometric if only if the eigenvalues of the matrix A associated to G1 the same as the eigenvalues of A2 associated to G2. Okay. Any questions? Okay, so now I like to consider everything in this double cover. So consider S3 as unit quaternions. Now, given any element or any quaternion, so given any x quaternion, then I could define a map that sends x to ax b inverse. So I multiply from the left by A and multiply on the right by B inverse. And this is a well-known double cover of S3 cross S3 to SO4. Okay. Now, remember we have these eigenvalues of the self-adjoint matrices. And when you only have one eigenvalues, the connected component is SO4. So you can write this as, you change to a different color, row of S3 cross S3. Okay. And when you have two distinct eigenvalues, you have row of S3 cross S1 with the isotropy group leaving the plane spanned by the two eigendirection of the same eigenvalue invariant. Okay. And we also have the three states, the isometry group, connected component of isometry group can be written as row of S3 cross 1. Okay. This in our paper is the, well, this is a quite, this is a convention people use, okay, bi-invariant. Okay. And this is something we call Berger, but not bi-invariant. And in the three distinct case, we call this generic. And now we have three different geometries. We have S3 with SO4, okay? And we have this geometry that comes from the Berger, but not bi-invariant metrics. And we have this one, which is what we call the generic metrics. Okay, so among those, only this one is the maximal geometry. Okay, and let me introduce the definition for maximal geometries here. So first note that all Berger but not bi-invariant metrics give us equivalent geometries. X1, G1 alpha 1 is equivalent to X2, G2 alpha 2 if you can find a diffeomorphism between X1 and X2 and a Lie group isomorphism between G1 and G2 and intertwine with the action. Okay. And among the geometries introduced above, only round metrics give us the symmetry maximal geometries. This is usually people call this maximal geometries. We add this word because we want to make the distinction between this and metrically maximal geometries. Okay, so XH beta is a subgeometry of XG alpha if if H is a subgroup of A, G, And if the action alpha restricted to H, give us the action of beta. Any questions?
Some are
Yes.
the generic metrics also equivalent geometries?
Equivalent geometries to what? Oh, yes.
You say that.
Yeah. Yeah. Sorry. Okay, so geometry is a maximal geometry, symmetry maximal geometry if it is not a subgeometry of other geometries. I should also mention that all of S3G, okay, these geometric structures, they are modeled on this geometry, okay, which is an example of metrically maximal geometries. Okay. So what do we mean by metrically maximal? It just means that you have largest.
Sami, another question, Sami.
Yes.
Doesn't equivalent, I assume, implies asymmetric or not?
No,
So
I
if
don't
two
think
metrics
so.
are equivalent, are they isometric?
No, I don't think so.
Oh,
Right.
it's just the group action. It's just the group
Yes.
action that's equivalent.
Right. Yes.
Ah, okay, okay. Sorry.
It's okay. So this is an example of what I was saying. Okay, so this is an example of metrically maximal geometries. So this basically just means that the amount of invariant metrics is largest. Okay. So how do we even begin to classify three-dimensional geometric structures? So we can start from this result by Sekikawa-Milner, which says that the universal cover of compact three-dimensional geometric structures are given by the following. So Sekikawa showed that either it is constant curvature space up to scaling, or S2 cross R, H2 cross R up to scaling, or unimodular Lie group with left invariant metrics. And result of Milner shows that these unimodular Lie groups are precisely one of the following. Okay. So SU2, Sol, Neal, the Heisenberg group. E2 is the rigid motion of the Euclidean plane. And I think you know what's SO2R and the R3. Any questions about this slide? Okay, so first then classify the maximal, or what we call symmetry maximal geometries. So up to equivalences, you have these 8 geometries. Now, I like to remind you that every geometric structure admits a metric that's modeled on the one of the Thurston's 8 geometries. However, it is not true that every geometric structure, every three-dimensional geometric structure is modeled on one of the maximal geometry. Okay. However, if you change the list a little bit, you can say that every three-dimensional geometric structure is modeled on one of the following metrically maximal geometry. Okay, so this comes from E2. This is a semi-direct product where this action is given by rotation, and the S3 geometry, H3 geometry, S2 cross R, H2 cross R, the Heisenberg group, SO2R, and the Sol geometry. Any questions? Okay, so then what we are asking here. So we let M.
Sorry.
Yes.
So the difference between your list and Thurston's list is that you pick the transitive group with minimal dimension, right?
Yeah, you want the smallest ones or largest invariant matrix. Yeah.
Mm-hmm.
Right. Okay, so now let's pick M1G1 to be a three-dimensional. You want it to be maximal or you don't want to be maximal, it's okay. Geometric structure. And you let M2G2 be a generic manifold. And now we assume that these two spaces are isospectral. And of course, the hard question is M2G2 also a geometric structure, right? In other words, can you hear local homogeneity in dimension 3? Unfortunately, we can't say much beyond Berger's beautiful theorem. And now let's stay within the local homogeneous manifolds. So now let M1G1 and M2G2 be two isospectral three-dimensional geometric structures. Now you can ask, are M1G1 and M2G2 locally isometric? Remember, in higher dimensions, this is not true. Okay. Are M1G1 and M2G2 modeled on the same metrically maximal geometries? In other words, we may ask, oh, can you sort of hear the universal cover of the three-dimensional geometric structures topologically? And then we can ask, when can we say that M1G1 and M2G2 are actually isometric? Of course, it is not true that M1G1 and M2G2 must be isometric because they are isospectral but not isometric hyperbolic manifolds. Okay. So here I'd like to mention a few previous known results. So in a preprint by Schmidt and Sutton and a paper by Emilio show that if you have left invariant metrics on SC2 can be mutually distinguished by the Laplace spectra. And I should also mention that this result it was recently extended to homogeneous spheres in higher dimensions. Okay. Okay, so now let's move on to the main theorem. So in our theorem, I'm going to let M1G1, M2G2 be compact isospectral three-dimensional geometric structures. And we already know from Berger's theorem that constant curvature spaces are determined by the Laplace spectrum, so we will not list them here. If M1G1 is modeled on one of the following metrically maximal geometry, okay, this semi-direct product geometry, S2 cross R, H2 cross R, or the Heisenberg neo-geometry, then the universal cover are isometric. Okay. So that's the strongest statement. And then we have the statement, if M1G1 is modeled on S3 geometry, then M2G2 is also modeled on S3 geometry. So lastly, if M1G1 and M2G2, here I want both spaces to be in the solid geometry, then the universal cover of M1G1 and M2G2 are isometric. Okay. So we couldn't quite distinguish spaces modeled on the sol and spaces modeled on SL2R, but we believe that if we can compute another heat invariant, we can resolve the issue. So we conjecture that if M1G1 is modeled, okay, so we conjecture that in any case, M1G1 should be locally isometric to M2G2. Just couldn't prove it yet. Any questions?
What about up to isometry?
Yes, we have some results here. Okay, I'll mention that in the next slide.
And
So
what about
oh,
SL2R geometry?
sorry. Yes, yeah. So first we have the result that you can hear locally symmetric three manifolds among all locally homogeneous manifolds based on the theorem above. And we also answer this question, when can we actually say that M1G and M2G2 are isometric? Let M1G1, M2G2 be isospectral three-dimensional geometric structures. If one of them is modeled on the Neal geometry or the S2 cross R geometry, then they are isometric. So here, to conclude the result on the Neal geometry, we actually use a result by Carolyn Wilson, which they computed the Laplace spectrum of Heisenberg three manifolds, and show that if you have two different, if you have M1 and M2 Heisenberg manifolds isospectral, then they must be isometric. Any questions? Okay, so here I'd like to say a few words about the method of the proof. So in the proof, we use heat invariance. Let me remind you what is heat invariant. So we start with the trace of the heat semigroup. Okay. And as t tends to 0, the heat trace has this asymptotic expansion. And each coefficient here is called a heat invariant. And we know that isospectral manifolds must have the same heat invariance. So by computing heat invariance, we might say a few things about isospectral manifolds. So here are some explicit formula for the heat invariance. The explicit formula below was given by Berger, Singer, and Sakai. And know that, oh, A3 is in the next slide, sorry. Okay, so here we only have A1 and A2. Know that using equation 5, 6, and 7, Berger show the theorem that given a constant curvature 2 or 3 manifolds are audible. And also, I like to mention that in Sakai's paper, we can actually have an algorithm for computing later heat invariance. So theoretically speaking, you can actually compute A4, A5, and so on. But the computation gets very, very difficult starting from A4. Here we have this formula of A3, and I sort of divide this into 3 parts. First part is this derivative terms, involves derivative of a curvature tensor, and A bar has 4 terms. It's actually a complicated polynomial degree 3 in R. And we also have these geometric quantities. So what was our strategy here? So now let M be a locally homogeneous free manifold. And we know that we can express A1 and A2 as volume times a polynomial in terms of eigenvalues of the Ricci tensor. Now, to compute A3, we divide this into 2 different cases. Note that from this result, Sekikawa, M is either locally symmetric or quotient of unimodular Lie group with the left invariant metric. Okay, so for locally symmetric spaces, we can say that this term d bar is equal to 0. Here. Now to compute the heat invariance for quotient of unimodular Lie groups with the left invariant metric, we use this frame we call Mueller frame. Okay, so you find orthonormal frame E1, E2, E3, such that these relations hold. Okay. All right, so let me explain what's the end game here. So now I start with M and M prime isospectral, okay, which means that their heat invariants are equal to each other. So I have the heat invariant AIM equals AIM prime for I equals 0, 1, 2, and 3, okay? So in the first step, we show that either M and M prime are both locally symmetric, or they are both quotient of unimodular Lie group with left invariant metrics. Okay, so M prime locally homogeneous, locally symmetric, or both M bar, M prime bar, universal cover are unimodular Lie group with left invariant metrics. The best case scenario is you can actually show that the equality of the heat invariance implies that they have the same alpha, beta, gamma, and you can also show that these lambda 1, lambda 3 are equal to each other. So best case scenario is you can find E1, E2, E3 on M, and E1, E2, E3 prime on M prime. And up to permuting indices, you have lambda 1 equals lambda 1 prime, lambda 2 equals lambda 2 prime, and lambda 3 equals lambda 3 prime. Okay. So why is this the best case scenario? So because if we have such frames, that means we can find a linear transformation, okay, going from the, So that means we can find a linear transformation. Let's call this phi. We can find the linear transformation from a Lie algebra of M bar to Lie algebra of M prime bar. Okay. Furthermore, since these constants are equal, we can say that this phi is actually a Lie algebra isomorphism. And this will induce, and the fact that you have orthonormal frame implies that this is actually an isometry, this preserved inner product. So this phi can be extended to a Lie group isomorphism, okay? Furthermore, it will be an isometry. So that's the end game. Any questions? Okay, for the last 10 minutes or so, I'd like to say a few words about our results on elliptic locally homogeneous free manifolds. So what do we mean by elliptic free manifolds? Just mean a compact manifold covered by a topological free sphere. So remember, we have this result saying that constant curvature spaces are audible among all Riemannian manifolds, right? But it's not that clear to us that if I have two spherical space form, they are an isospectral, then they must be isometric. And here is a theorem by Ikeda, Yamamoto, and Ikeda. They show that if you have M1G1 and M2G2 isospectral spherical space forms, then they are indeed isometric. So now the question is, given two isospectral geometric structures modeled on S3 geometry, in other words, the universal cover is SE2 with a left intervariant metric, can we actually say that they are isometric? So I know this sounds like a very classical problem, but we couldn't find this classification in the literature. So we kind of just did it ourselves. So now let M be a locally homogeneous elliptic three manifold, okay? And we obtain a metric classification of locally homogeneous metrics on M. So I'll show you the table later. Right now, let me just say that given any M equals S3 quotient this group gamma, an isometry class of left invariant metric induce either 0, 1, or 2 isometry classes of metrics on M. And you have one isometry class covers two isometry classes only when the group you're looking at is cyclic of order at least 3, okay? And G is Berger, but not bivariant. Okay, so here comes the table. Okay, so I like to focus on this case, okay, and this case. Okay, so when you have cyclic groups, things could be quite interesting. So when you have gamma Q1P, P is positive or -1, you could have two isometry classes where precisely one of them is homogeneous and the other is not. And here, if P is not congruent, P squared is not congruent to -1, then you have two isometry classes, but neither is homogeneous. But if P squared is -1, then you have one isometry class. Okay, so here we like to think referee will point out that we actually have this case P squared equals -1. It's different from the case P squared not equal to -1. Any questions about this table?
So could you explain how you get the two different isometry classes in the quotient?
Yes. Yeah. So let me explain that here. Okay. So remember, when you have a Berger but non-constant curvature metric, and then the connected component of the isometry group looks like this. Okay. So now let's take gamma Q1P as an example, Q11 and gamma Q1 -1 as an example. So one of the cyclic group is contained in the first vector. Okay, so if you lift these to S3 plus S3, then one of the, I forgot which one it is. Okay, but one of them, let me just note by gamma tilde 1 to gamma tilde 2. So what I'm doing is I'm lifting these two groups through row and obtain two different groups. They're isomorphic though. Now, one of the group is inside the first vector, and the other is just inside of the second vector. So based on this result, I think it's by Wolf, that if you look at the centralizer of, kinetic component of centralizer, if it acts transitively on the universe cover, then the space is homogeneous. If not, then it's not. Okay, so if you compute the centralizer and the connected component, you see that one group acts, the centralizer, one of them acts transitively on the S3 and the other doesn't.
There's an orientation reversing isometry that switches the two S3 factors. Why doesn't it give you something isometric?
Right. So if your two lattices are only conjugate through orientation reversing, only conjugate through orientation reversing elements in S and O4, then you will have something like this. You have two different isometry classes.
So after isometry, it's really the same metric. It's just equivalent to each other by an orientation reversing isometry. Is that what you're saying?
No, it's not. It's not isometry. Okay, so I'm saying that these two lattices, if they are conjugate through only orientation reversing elements inside of O4, then this kind of thing happens. So in this case, you can definitely show that these two spaces are not isometric because one of them is homogeneous, the other is not.
That's strange.
Yes. Yeah, so if you feel strange, you could try to compute the centralizer inside of this isometry group, and then you can definitely see one of them acts transitively and the other doesn't.
So essentially, you're labeling the spaces by the isomorphism class of gamma, right? But then the embedding of gamma into the isometry group, I
Yes.
change the quotient, of course. So that's what's
Yes.
happening here. It's
Yes.
a different embedding of gamma inside the isometry group.
Yeah.
Okay.
But what's interesting is if you consider this under constant curvature spaces, then you only have one class. Okay. All right. So we also obtained the following extension of this result on SU2, right? So now fix a subgroup of SO4. Now consider a collection of locally homogeneous metrics on the quotient. There exist at most two isometry classes of metric with the same first four heat invariants. Furthermore, you can show that if gamma is not cyclic of order at least 3, then isometry classes of locally homogeneous metrics on M can be mutually distinguished by the Laplace spectra. So before we consider all left invariant metric on SU2, now you can look at all locally homogeneous metrics on S3 quotient by a group. Okay, so I'd like to repeat this example again and remind you that, tell you that because we have this example where one of the space is homogeneous and the other is only a locally homogeneous space, so we see that we cannot use a heat invariance to determine whether homogeneity is an audible property in dimension 3. Okay, because they have the same heat invariance. So our current project is to use wave invariance to determine whether these two spaces are isospectral. And what if we allow the fundamental group to vary? We have this following result. If M1G1, M2G2 elliptic locally homogeneous free manifolds, same first four heat invariance. If one of them is not, if they are not locally isometric, then their fundamental groups must have different orders, which will be very strange. Okay, that's all I want to say for today, and thank you very much for coming.
Thank you. Thank you for a very nice talk. Are there any questions?
some, and so you don't know if these very particular length spaces are isospectral, because the fundamental group are cyclic, right? They are length spaces. And
Right, we don't know yet.
okay.
We suspect that the wave invariance would give us an answer.
And what about some lower eigenvalues? Have you tried computing?
Yeah, so I mean, the eigenvalues, lower ones, is computable for the universal cover. It's not that clear to me where are the invariant ones. Yeah. So I look at the eigenfunctions,
yes, because
right?
yes.
From the from the theorem, Peter-Weyl theorem, and then you could try to see where it goes.
Yes, because the first eigenvalue of the sphere might not appear in the spectrum of the quotient, right?
Yes,
so
that's exactly.
Okay, very nice talk. Thank you.
Are there other questions? Actually, I kind of have a question on this last theorem here. So if I'm trying to wrap my head around this, if they have the same first four heat invariants, some particular same total scalar curvature, so then their universal covers, which are metrics on the sphere, would actually, and they're homogeneous, and so one would have scalar curvature that's actually a multiple of the other. They wouldn't be the same. Yeah, that sounds very.
Yeah, I mean, the scalar, the Ricci tensor is quite generic in this case, so you could have a lot of possibilities for summing up to the same thing. X plus y plus z equals 1, basically.
Yeah, okay. Huh. Are there any other questions? Okay, well, thank you again.
Thank you very much for coming and the invitation.
Oh, and the next talk is in 2 weeks. It's 3 hours later, whatever time this talk is for you. The next one is 3 hours later, and it'll be by Romina Arroyo.